Now for the final, but also most important thing that you will learn about DAX today, which is the basic patterns. So we've looked at fairly complex DAX already, but as it turns out, for analyzing DAX, what we can do is disentangle or split them up, and then we will always find like one of several basic patterns, and here they are. So it's a confounding pattern, a mediating pattern, and a collider pattern. So let's start by considering the confounder. It's also called fork because the idea is that, like, just in a fork, you have a node here. That's pretty much like what we consider here as what makes it a confounder, which is the x. And the x is in a particular relationship to our treatment and outcome of interest, which is d and y. And the causal arrows go both into d and y. That's why it looks like a fork. Well, my fork here has 4 outgoing arrows, but here we have obviously only 2. So the question mark shall just indicate that, yeah, we might be unsure about the causal relationship, sorry, between D and Y. Another way to represent this, and you will see that in text, is we start with D, our treatment, but then there is an ingoing arrow into D coming from X, and like the chain continues with an outgoing arrow from X into Y. So that's the confounder. Then we have the mediator, and the only thing that's changed here is that we have now 2 outgoing arrows from D, one going directly to Y and the other one going through X, so to speak, right? So we have D to X and then X to Y. And in such a setting, we would call X a mediator, and this pattern of D to X to Y, we would call that chain. So maybe it's time for a little example here. So say D is our income. Oh, sorry, like D is our education, Y is our income, and what could be X as a confounder? Well, that could be your your heritage, right? Or your parents' education or your parents' income, right? Has an effect on both your education and on your maybe present but also future income. What about X as a mediator? Well, if D is education again, how does D travel to Y? So how does education make you maybe more prosperous or richer in the future? Well, because education makes you more attractive on the job market because you like gain additional skills, right? So X could be skills or just chances on the job market. And then we have a final pattern, which is in which X is a collider. So here we have 2 arrows, one going from D to X and the other one going from Y to X, and they collide in X. That's why it's called collider. It's also called inverted fork because now, yeah, both arrows go into our X variable. Now, what could be a good example here? So if D is education again and Y is income, you have to think about something that is both affected by your education and maybe also by your income. Could be probably being admitted at Harvard, right? So if you want to get admitted at Harvard, what helps is maybe um, your educational background, but certainly also your financial background. Now, this is a highly problematic pattern when you are in fact interested between between the relationship between D and Y, and then you're tempted to control for X because, well, bad things can happen here. But more on that later. So let's talk a little bit more about confounders. So confounder is probably what you are already most familiar with because, like, that's the common thing we worry about before we start to say control for variables in a regression. So the idea is that a confounder induces a statistical association between its effects. So say X is positively correlated with D and also positively correlated with Y. So it makes, like when X grows, it makes both D and Y bigger. Now, when just looking at D, this would also mean that we observe a positive relationship between D and Y, but this could be entirely due to X. Now we learn the first thing we can do and how this changes our interpretation in a DAG, which is we can condition on a confounder, parentheses, or a descendant of a confounder. We will consider that later. And when we do that, it blocks the path. We will learn much more about blocking paths and like isolating the causal effect of interest in a causal graph setting later. But here the idea is when we can measure X, we can control for it, we can block it. We would usually indicate that by drawing a box around a variable. And then there is no information flowing, so to speak, from D to Y via X. And what's left then is the actual causal effect here between D and Y. If we don't condition on a relevant confounder in our setup, this would then induce non-causal statistical association or omitted variable bias. On the right-hand side, you see an example of a confounder X that is, you could call it like mediated by another variable W. Now, if we control for that variable W, we would block the path as well. Here's a more concrete example how confounding works and how conditioning on a confounder works. So in analogy to the previous graph, we have Y, which is on the Y-axis income, measured on some arbitrary scale. Then we have shoe size as our treatment of interest, which is D, or like the X-axis here, which is probably confusing because there is another third variable that I called X, which is gender. And gender is not indicated as one of the axes, but is indicated by color. Now, when you look at the left-hand graph and ignore the color for a moment, you might be tempted to assume that there is a causal relationship between shoe size in our sample and income, right? So we see the positive relationship in the dots, but also in the fitted line. Now, do we really believe that there is a causal relationship between shoe size and income? Well, I'm sure there are some silly studies out there published in like high impact outlets, but well, that's probably a little bit fishy. Now, what could be the reason for this statistical relationship that we observe? Well, one suggestion would be gender, right? So what we already see is that both income and shoe size are on average lower for females than for males. So for shoe size, we would uh, trace that back to biological reasons. For income, we might trace that back to, well, a structural bias in income, structural gender bias in income that we observe in many societies, unfortunately. So what happens when we condition on that? So that's illustrated on the right-hand side. This basically means that you want to look at the relationship, but separately by the different variables of gender. So in this case, just female and male. And what happens then is that the relationship disappears. We, in fact, have two relationships, so one for males, one for females, and the lines are just flat. So again, while gender induces a statistical relationship between shoe size and income, once conditioning on this confounder or common cause, as we can also call it, the relationship disappears. What we'll still see, of course, and you see that in like on the income axis, is a quite substantive difference in the incomes between females and males. And you could say that's the gender bias that we observe in the data. Now, briefly on the two other basic mechanisms here. So mediators. Mediators are interesting because they allow us to express mechanisms. So how the treatment affects the outcome more specifically speaking. right? One example could be that, back to our coffee example, coffee as a treatment leads to better stats exam results. Why? Well, but why is that? Maybe because there's a mediating variable sort of built in coffee, which is caffeine, which stimulates the nervous system and then also prevents drowsiness and therefore leads to better stats exam results. Right? Now, unfortunately or fortunately, a cause and effect relationship can be mediated by multiple mediators. So probably it's not only caffeine, but also the fact that you just drink something, or just the act of drinking, or like the social component to it. So many potential reasons. And what makes it even worse, at least from a technical perspective, is that the mediators themselves can also be causally connected. And when they then start drawing the graph, things can get really messy. Now, why are mediators both interesting and also potentially problematic? It's because in most cases, when you are mainly interested in the net effect of D on Y, or not the net effect, but the total effect of D on Y, you would not want to condition on the mediators, because this would induce so-called post-treatment bias, or to put it differently, it would take away some of the effect that you are actually interested in. If that sounds complicated, no worries, more on that in the next session, because this is a fairly important pattern. Down there, you see another example of that. So fire ultimately causes the alarm bells to ring. Why is that? It's not because of like the fire itself, but by the smoke that it causes, right? And then the smoke, and you like make it even more complex, right? So going into the mechanics of the alarm. Now for the final key pattern, which is colliders. Now, collider settings are, again, ingoing arrows into another variable and outgoing from the treatment and the outcome of interest. So in other words, they let us express how two variables jointly affect another variable. So what's the problem about colliders? The problem is when we start conditioning on them by, for instance, in a regression, just adding them as another control variable. This would induce statistical association between the two contributing variables here, D and Y. And this would give rise to collider bias, which is also known as Bergson's paradox. Again, more on that in the next session. So here's an example. So assume that talent and beauty are independent in the population. So there are talented people, there are beautiful people, some people who have both, some people who have none. But each of them causes someone to become a movie star, at least in the extreme, right? So you can be extremely talented, but not particularly beautiful, can still turn into a celebrity. Or you can become a celebrity by just being beautiful, but you lack the talent. What's probably least likely is if you lack both talent and beauty, um, might make it difficult for you to become a movie star. But we could also argue about that depending on your taste. So I'm thinking about guys like Nicolas Cage probably lacking both, and nevertheless turned out to be a celebrity. So why is that problematic? Because again, well, it's not problematic, right? So it's an interesting pattern, a plausible causal pattern. But if you're interested in the relationship between talent and beauty, and then condition on celebrity status, which in practice could mean that you just study a sample of celebrities to look into the relationship of talent and beauty, things can go pretty weird. And one consequence is, well, maybe find out yourself. So the question would be, what's the correlation between talent and beauty for a sample of movie stars when we compare to the population as a whole? So which is stars and no stars combined. All right, we will find out soon. We've almost come to an end. A final question to consider is how to actually analyze graphs after we've learned how to, in principle, draw them and interpret basic patterns. Well, here's the basic process in a couple of steps. So you would start and draw the DAX, and that's probably where like most of your intellectual energy should go into it, right? Because like, again, it involves thinking about theory, observations, empirics, and so on. Then you would draw it, revise it, draw it, revise it. And then you would start to look at it and find the causal and the non-causal paths between D and Y. So we've talked about causal paths, and we'll talk much more about the non-causal paths in the next sessions. Now, once you've identified those paths, you then work out the conditions or the set of variables that meet the so-called adjustment criterion with respect to D and Y. Again, more on that next week. So the idea is, what should I have to control for or take care of to, well, adjust my procedure, adjust my model in a way that allows me to do causal inference with regards to the relationship between D and Y. As we will learn, there might be shortcuts. This refers to the so-called backdoor criterion, but in principle, we will have to look at the entire graph to also identify these shortcuts. Now, this work can be tedious, particularly with complex stacks, and you will see a couple of those. But we will learn how to do that in the next sessions. And you don't have to do that by hand. I personally recommend to draw your DAGs by hand because at least in my case, like there's a good link between like drawing and your mind. But there's also software that can do that for you. And in particular, that can help you work out those conditions in the earlier steps. R is well suited to take care of that, and you will learn how to do that in the labs. Now, I've made some references in the beginning to like different traditions with regards to the use of DAGs, but also with regards to the use of the potential outcomes framework. And like, I don't want to emphasize these differences too much, but they are existing, although they are probably not exactly on the rise anymore. So here are just like two quotes, one from the econ camp and one from the causal graph camp. So let's look at the econ camp first. Imbens and Rubin, so two yeah, really like key players in the econ camp with regards to propounding the potential outcomes framework. So they comment on Perel's work as being interesting. Many researchers find his arguments that path diagrams are a natural and convenient way to express assumptions about causal structures appealing. In our own work, perhaps influenced by the type of examples arising in social and medical sciences, we have not found this approach to aid drawing of causal inferences. So that's one of the perspectives in one of the camps. And Pearl, commenting on that, is writing, so what is it about epidemiologists that drives them to seek the light of new tools, why economists seek comfort in partial blindness while missing out on the causal revolution? Can economists do in their heads what epidemiologists observe in their graphs? Can they, for instance, identify the testable implications of their own assumptions? Can they decide whether the IV assumptions are satisfied in their own models of reality? Of course they can't. Such decisions are intractable to the graphless mind. So you see what the conflicts are. Now, I don't invite you to become part of that conflict because I think to a certain extent it's really pointless to argue about these things. But there is certainly some truth in it that in some scenarios, potential outcomes framework is more suited than causal graphs. And in other scenarios, it might be the other way around. So um, my perspective and other people's perspective on that is that graphs are particularly useful to discuss complex variable constellations. So whenever you deal with like not clean experiments, but really like multiple variables in an observational setup, but also selection mechanisms or maybe measurement problems, yeah, result your graphs because they're really useful there. The potential outcome framework, on the other hand, is particularly useful when thinking about treatment assignment mechanisms in the context of experiments, but also quasi experiments. More on that in the next sessions.